Hi, everybody. I'd love to introduce Samuel Blau from the Berkeley lab. And he's been doing a lot of work on, well, creating data sets and models of molecular dynamics and making them available for machine learning. Welcome, Samuel.
Thanks so much, Greg. Thanks for the invitation. Thanks, everyone, for being here. I'm really excited to tell you today about the Biomolecules 2025 dataset. A lot of work went into this, and we're really excited to be sharing it with the community. So I am a computational chemist, which means that I run atomistic simulations. And kind of what that means in a nutshell, you can imagine you have some 3D atomic positions, and you can then predict the total energy and the force on each atom. And then you can update your atomic positions and repeat this iteratively. This is kind of the general workflow of atomistic simulation. And we do this to kind of learn a few different things. We can simulate the molecular dynamics of a box of atoms. We can simulate find the optimized geometry and the free energy of optimized geometries of certain collections of molecules. And together we can kind of elucidate complex reaction pathways and understand the time dynamics of how a system evolves under realistic conditions. And this is kind of the heart of what it means to run atomistic simulations as a computational chemist. So then the question becomes kind of how do we calculate the energy and the forces that we need in order to drive our simulations? We can use a classical force field, which kind of just parameterizes different interactions with analytic terms. And classical force fields are typically quite fast, but they struggle to describe chemical reactivity. Then the other kind of end of the spectrum is density functional theory, where you're actually solving an ansatz to the Schrodinger equation, and you're actually kind of accurately describing the electronic structure and how the electrons move and then how the nuclei move under the influence of the electrons. And I would say that DFT is quite accurate, but very slow. And it actually scales typically as the number of electrons cubed. So if you double your system size, then you 8x the cost of your simulations. And then we have what are called machine-learned interatomic potentials, which have become very popular within the last 5 years. And they are trained on density functional theory data, and they kind of have the promise of giving near DFT accuracy at near classical force field speed. So suddenly you can actually simulate large boxes of atoms for large length scales and time scales, but with this kind of quantum chemical accuracy. And that has a lot of people in the community very excited. And just kind of as a comparison, this is a figure from one of Alexander Isayev's early MLIP papers. A DFT calculation that would take 52 core hours on a GPU takes a fraction of a second, just kind of showing the acceleration that ML can offer in this case. But the kind of MLIPs can provide thus otherwise intractable atomistic insight, but the domains in which they are reliable depends on the available training data. And this is kind of something that we all know about machine learning. It's all about the data. If you have a large, diverse, and high-quality data, then you can build really powerful machine learning models. So, a lot of this kind of general machine learned interatomic potential development has focused on materials. So this is a very well-known leaderboard called MatBench Discovery. So the materials project is kind of a long-running database repository of simulated materials information. In 2022, they released the MP-Traj dataset for training these machine learning potentials. And then in 2023, they put out this leaderboard, which kind of has a bunch of different metrics that I'm not going to go into, but kind of metrics of the utility and the quality of machine learning potentials trained on the data. And I just want to call out this MACE MP0 model. This was back in kind of mid-2023. But MACE MP0 was kind of just trained on these crystal unit cell relaxations. So small boxes, periodic boxes from kind of inorganic materials. But the machine learning potential, MACE MP0 trained on this data could actually simulate qualitatively a staggering diversity of systems, from kind of hydrogen combustion to aqueous interfaces, batteries, metal organic frameworks, things that were clearly far outside of the chemical regime of the training data contained in MP-Traj. And I think this was like a wake-up call for a lot of people in the community, and certainly to me as a contributor. I think people before this were really thought of MLIPs as being quite limited to specialized cases, kind of trained on small bespoke data sets. And I think MACE MP0 was the kind of the spark that kind of ignited a lot of imagination and enthusiasm about the ability of these things to generalize and be super useful. And thus we've the paper has gotten over 300 citations in less than 3 years. It's really been a game changer. Now that was back in the middle of 2023. We see there's lots of now better models trained on the same data set, but at a certain point, architectural improvements can only get you so far, and it really comes back to the data. And here, all of these models are trained on the exact same data set, NP-Traj. But in 2024, a team at Meta, the FAIR chemistry team, released the Open Materials 2024 OMat dataset. And OMat was over 60 times larger than NP-Traj. It has much higher forces, so you're sampling geometries that are off equilibrium, further from minima of the potential energy surface, more diverse sampling. And they released it freely to the community. And now if we look at the MathBench Discovery Leaderboard, we see that all of the best models are also trained on OMat, which is to say that if you have more data and better data, your models get better. Again, thoroughly unsurprising from kind of trends in machine learning that we're aware of. So at this point, I would say it's generally accepted in the computational chemistry and computational materials community that atomistic simulations of well-behaved crystal materials should always start by using a pre-trained MLIP rather than going to expensive density functional theory. And that's really a paradigm shift, that is fundamentally different from how people have treated these types of problems over the preceding 3 decades. So this team at Meta, this FAIR chemistry team, has actually done a lot for the community. They've released quite a few data sets and contributed, all fully open source. So originally they were kind of focused on catalysis. In 2020 and 2022, they released catalysis data sets. In 2023, they released a metal organic framework data set with CO2 absorption for direct air capture. And then, as I mentioned, in 2024, the OMat materials data set. And each of these were on the order of about 400 million core hours, which is really beyond what an academic lab can do on DOE resources. And that's, we really have to kind of tip our cap to the reality that kind of these tech companies have resources that outstrip really kind of government-led efforts. And we kind of have to be, I think we should be very grateful to this team at Meta that they released these data sets fully open source. But there's clearly something missing here if you kind of look at this timeline, and that is molecular chemistry. And so I was quite excited when in late 2023, my friend Brandon Wood, who's a member of the FAIR chemistry team at Meta, came to me and pitched this idea of making a large molecular DFT data set to try to kind of fill this big gap and push the whole field forward. And that's why I'm so excited to tell you today about the OpenMolecules 2025 data set, as well as models and benchmarks that I'll describe. So OpenMolecules 2025, or OMol, as I'll refer to it, is really, and I think at this point it's being accepted that it's going to kind of unlock machine learning potentials specifically for chemistry. And this was a massive effort, a collaboration between Meta, Genentech, Berkeley Lab, Los Alamos, and 6 researchers from 6 different universities that, Meta and I kind of were the co-leads on.
So question.
Please.
I'm trying to differentiate the complexity of this one to the previous ones. It sounds like those are smaller molecules, or just the catalysis, like tiny things that just connect to each other and just like catalyze each other, whereas these are like protein scale molecules.
So it's not that the number of atoms contained in snapshots in previous data sets are small. I mean, they are smaller than what's in the open molecules, but they're just fundamentally different. Like this is adsorbates on surfaces. This is kind of adsorbates inside of metal organic frameworks. These are bulk materials. All 3 of these were periodic DFT. So you kind of have periodic boundary conditions. You're using a plane wave basis set. And so you're kind of limited in the level of theory that you can do. For open molecules, you're now in a localized basis set. So you do not have periodic boundary conditions. And you're dealing with, things like small molecules, electrolytes, biomolecules, and metal complexes. And with a much higher level of theory, a more accurate level of density functional theory than you can run in a periodic simulation. So these are kind of just chunks of molecules, kind of collections of molecules in a localized basis, but with varying charge and spin, and kind of dealing with reactivity, solvation, different length scales of interactions, and we kind of sample the geometries with a variety of strategies. So Was much more expensive. This data set cost over 6 billion core hours, which is kind of more than all the previous ferrochemistry data sets put together. Just kind of as a point of reference, like a DOE supercomputer, the CPU partition of the Perlmutter supercomputer puts out about 2.5 billion core hours per year. So this is like 3 DOE supercomputers working on one project exclusively for a year.
Okay. And it sounds like the main complication is, one, there's less regularity. So you have to account for more phenomena. I'm thinking like hydrodynamics versus magnetohydrodynamics. You have just more physics to model, and you can do like bulk assumptions, so extra compute. And it sounds like the variability of the space is much larger, so you have to do way more samples.
Yeah, I mean, I think it's hard for me to make like a concrete statement about like the complexity of molecules being larger than the complexity of materials. The 3 previous data sets were very much more in kind of the catalysis, different approach, different types of systems, and we have different electronic structure tools available to us as far as the kind of level of accuracy. So yeah, I mean, you can simulate electrolytes in a periodic context, but then you're limited to using the best kind of density functional theory that we can do in periodic systems, which is much lower quality than what we can do in a localized basis.
Got it. Okay.
Also, in a periodic system, you are basically inherently limited to being overall charge neutral, versus in a localized context, you can have net charge. And that's quite important for kind of describing complex chemistry, where you care about reactions happening or systems where there may be locally net charge.
Got it. Okay. Thank you.
Of course. So this was a really massive effort. And, for the computational chemists in the audience, like this is basically the gold standard molecular DFT settings that one would choose. It's, basically Martin Head Gordon's best functional and an excellent triple zeta basis set in a particularly tight integration grid. So really, really high quality data here that we've generated, and we've saved a ton of properties, which I'll mention a little bit more later. But we really think that this data and the models trained on this data can be transformative for medicine, batteries, manufacturing, climate, and the fact that we have snapshots up to 350 atoms and 83 elements of coverage is just far beyond anything that's been done before, as I'll describe in a little bit more detail. And again, everything is fully open source. So first we have to kind of throw up this periodic table heat map. So, molecular data sets to date have really been quite limited in elements. Kind of the most well-known ones are AIMnet2, which has only 14 elements of coverage. SPICE2 has 17 elements of coverage. A recent data set from a team at Google, QCML, did kind of for the first time extend far up to 79 elements, although it has major limitations, as I'll mention in a little bit. And OMol has 83 elements of coverage. And you hear every number on the table is the number of snapshots with that element present. So we really have quite strong coverage of even kind of these complex, rarer elements that you typically don't see in these types of data sets. As far as charge that I mentioned before, we go from a net charge of -10 to +10, so kind of a huge range of charge, and up to 10 unpaired electrons, which would be a spin multiplicity of 11. Just to give you a sense of previous data sets, SPICE had from -8 to +2, but all singlet systems, no unpaired electrons. AIMnet2, again, no unpaired electrons, but in this case from -8 to +8. QCML does have some radicals, but more limited charge. These all kind of pale in comparison to the vast complexity that we cover in OMol, with just a huge range of charges and spins. And charge and spin are really central to so much of chemistry, so much of molecular chemistry, from catalysis to reactivity in batteries, and et cetera. We also go up to 350 atoms in each snapshot. And remember that DFT scales as the number of electrons cubed. So these were very expensive to run these larger snapshots, but that's also central to being able to kind of describe complex chemistry. For comparison, AIMnet2 had up to 80 atoms, SPICE2 had up to 110 atoms, and QCML that I mentioned before, which really kind of expanded the elemental space, had only up to 26 atoms, only a single molecule. And that's like a really huge drawback. When we were kind of discussing this in the Open Molecules team Slack, the co-first author, Daniel Levine, said, really the richness and challenge of chemistry is mostly in the intermolecular interactions. And so if all you ever have is individual molecules, you're really going to miss all of that. But the ability for us to go up to 350 atoms in each snapshot means that we can get kind of proteins, ligands in protein pockets, which is central to how we describe kind of drugs and key biochemical function. We have kind of metal complexes with these shells of ligands all around them, which are central to separations and catalysis. And we have large chunks of electrolytes with these charged molecules that are central to electrochemical manufacturing and batteries. And we have large enough systems to really capture the interplay between intermolecular and intramolecular interactions that really govern chemistry. Also, just as far as raw size, compared to kind of some of the most well-known molecular data sets, we're basically 2 orders of magnitude more total atoms simulated. Compared to the largest previous data sets, we're still over an order of magnitude larger, basically. And not only larger, right, but also higher quality, better density functional, better basis set, tighter integration grid. So the ability to go kind of larger and more diverse and higher quality at the same time is really quite unique, and a tribute to the resources that Meta was willing to put towards this project. So now I just want to talk a bit about how the data set was constructed. And we kind of are going to have 4 different pie charts that I'm going to show. And the first one is, let's stand on the shoulders of giants, right? People have done a lot of work building data sets previously, and we wanted to leverage that. We didn't want to reinvent the wheel wherever possible. So we basically took a few data sets like Transition 1X, OrbNet Denali, Annie2X, and Spice2, and we just recomputed them, the exact same structures at our higher level of theory for consistency. Then we took a data set called Geom from Rafa Gomez-Bombarelli's group, and we basically did kind of Boltzmann rattling on the positions, and we did geometry optimization. Not too many steps, just a handful of steps. But these are kind of these drug-like molecules, and the Geom data set has been widely adopted, particularly by the generative ML community in chemistry. We took the RGD1 data set from Brett Savoy's group at Notre Dame. These are reactant transition state product trios. And we did kind of this interpolation from reactant to transition state to product. So for each of the 120,000 reactions, we generate 18 snapshots along this reaction path. Capturing kind of reactive geometries where bonds are in the midst of breaking and forming is central to ensuring that our machine learning potentials will be able to capture real reactive chemistry. We got advanced access to the Annie1XBB data set from Alexander Isayev. Again, BB here is for bond breaking. So this is more about bonds falling apart and coming together. We also ran a subset of that data set as triplets. We took the solvated protein fragments data set originally built by Oliver Unke, who's now at Google. And these are kind of small solvated protein fragments, as the name would imply. In 10% of the cases, we added an extra electron. In 10% of the cases, we removed an electron to create radical anions and radical cations. And then we did up to 3 optimization steps atop these structures. Finally, there are these MECDBs, mechanistic databases from a couple of groups at UC Irvine, where they have elementary reaction steps that are both radical reactions and polar reactions. And here we built a kind of a pipeline that we reuse over and over in a few other places in the data set. Again, this is about generating reactive snapshots. So we kind of know the endpoints of the reaction, we know the reactants and the products. But these are all just kind of graphically defined. We don't have any 3D structures. So we generate 3D endpoint structures using the Schrodinger suite. We then use a method called applied force induced reactivity, or AFIR, where you basically add artificial forces to pull apart the bonds that you expect to fall apart, going from reaction to product, and to push together the atoms to form the bonds that you need to be formed. And then we use the Mace MP0 pre-trained MLIP as our potential energy surface. And this basically you keep ramping up these force constants so that you pull apart the bonds you want to pull apart, you form the bonds you want to form, and in this way you can sample along kind of a reactive trajectory, a reaction path. And then we basically go along this whole path and sample dissimilar high energy and high force structures, which should be kind of the most reactive, if you will. So these were kind of all us either directly recomputing or riffing on previous data sets that people had built. This is about a quarter of OMol overall.
So question, when you say recomputing, can you describe kind of your computational framework, kind of the assumptions you're making, or how it's different from the simulations others have used?
Yeah, so as far as the 4 data sets where we just straight up recomputed, right? We literally take their geometries, the XYZ position of each atom and each snapshot has a list of atoms and their 3D Cartesian coordinates, right? And then you have the total charge and the total spin on that snapshot. And then we just simply, we use the ORCA computational chemistry code. This is a localized basis DFT code. We simply run the DFT, which is to say that we converge the electron density. And that's basically solving this ansatz to the Schrodinger equation, which gives you the total energy of a configuration and the force on each atom in that configuration. We also save the wave function, the dipoles, partial charges and spins, and kind of lots of other information that's either already released or will be released in the near future. But essentially, this is just kind of the simplest thing that one can do as far as electronic structure is calculate the total energy and the force on each atom. What makes what we did better is that it's a higher quality description of the electronic structure, a higher level density functional, more accurate density functional, a larger basis set, which again allows the kind of electronic configuration to be more realistic and more flexible, and a tighter integration grid, which means the precision of our energy and forces is tighter, which is important for the MLIP training. So it's just, kind of the same general DFT procedure as previous people would have done, just a more expensive, higher quality version of it.
Okay, makes sense. Thank you.
Yeah. So then,
I have a question.
Please.
OMol25 is composed of many existing datasets. What percentage of its data is new or was first introduced in OMol25?
Yeah, so here, since the community slice of the data set is 24%, right? So I would say 76% is like all completely new. But even here for there's only 4 slices of this pie, transition 1x, orbit denali, anti-2x, and spice 2, where all we did was exactly recompute the previous structures, right? Every other one of these was basically, as I said, riffing on previous data sets, kind of doing additional operations to add diversity or add complexity to previous data sets. I mean, no one had ever done anything with the MECDBs for machine learning potentials before, right? Those were data sets of reactions. We built them into geometries to run DFT on, to include in the data set. So, I mean, your call, what you say is completely new versus not. Like, we're calling this pie the community pie, because we're leveraging work that people had done previously. And the next 3 slides, I'm going to talk about kind of the 3 areas that we focused on, which were entirely new, entirely generated from scratch.
Oh, thank you very much.
So the first area kind of the 3 that we focused on in building OMol was biomolecules. Obviously, I think we all know the importance of biomolecules, given that we are literally made of them. And we've known that kind of machine learning has had great success in the utility for biomolecular simulations and predictions, of course, with AlphaFold 2, the Nobel Prize winning AlphaFold 2 being the most notable example. But there's a lot of interest in having an accurate machine learning potential describing things like protein ligand binding and protein-protein interactions. But these are inherently larger snapshots that people had not really gone to this level of depth before. So we basically, let's start with kind of protein ligand snapshots. We took all, I believe at the time, it was 700,000 something experimental protein ligand structures in the protein data bank. And we ran molecular dynamics on those simulations at different protonation states and cut out those structures to run DFT on. We also docked new ligands. We were unsatisfied with only 700,000, even if you had some different protonation states. We basically took artificial kind of drug-like molecules and docked them into the same pockets from the protein data bank, and also then ran MD on those and took snapshots out to run DFT on. We similarly mined the PDB for kind of protein nucleic acid structures, protein-protein structures kind of at the interface, like near solvent, protein-protein structures in the core of a protein, and all of this, again, different temperatures of molecular dynamics that we ran, classical molecular dynamics to generate these snapshots, as well as different protonation and tautomer states. Then halfway through the data set effort, the data generation effort, we took the first part of the data set, we trained a machine learning potential just on the biomolecules component, and then we used that to run MLIP molecular dynamics on other structures that would basically generate more diverse configurations. This is kind of like a pseudo active learning type of approach. We're not directly guiding towards uncertain regions, but at least by pulling structures from MLIP-MD, kind of with the first half of training on the first half of the data set, we access additional diversity. We then kind of also were really interested in doing metal complexes. So this is where we get a lot of that periodic table coverage. Now, metal complexes, these are central to, they are central to biology, but especially to separations and catalysis and kind of lots of chemistry that I think is going to become really important in technology in the coming decade. And here you're dealing with, what we did is we took the crystal structure database, the CSD, and these metal complexes basically will have one metal in the center surrounded by ligands, organic ligands. And you can have these metals at different charges and different spins with different kind of numbers of ligands around them. So we basically mined from the CSD all the possible metal oxidation state coordination number pairs or kind of sets of parameters, which you can see is a lot. Many metals, manganese can exist in 5 different oxidation states. Each oxidation state can have a variety of different coordination numbers, which is the number of kind of ligands kind of interacting with that central manganese. And we sampled all of these with quite a lot of diversity and thoroughness. We also took the ligands from the crystal structure database and sampled them. So we have kind of different types of metal coordinating atoms. We slightly oversampled the smaller ligands in the name of getting more data. We kind of slightly oversampled lower denticity, which is to say a ligand with only one atom that's directly interacting with the central metal versus 2, 3, or 4. We certainly have coverage of 2, 3, and 4, but we slightly oversampled the monodentate ligands. And then also ligands of different charges. And then finally, we took template reactions from 3 data sets where people had established kind of well-known or kind of classic metal complex reactions. Here are these MOBH35, MOR41, and ROST61. So this will give you about 135 metal complex reactions. And we then swapped out metals in them, and we swapped out ligands in them to generate hundreds of thousands of metal complex reactions. And then we used our same AFIR framework as before to sample reactive snapshots along these reaction pathways. And this kind of gives, we have different spins, high spin, low spin, and again we also did the same type of MLIP-MD where we trained a model on the first half of the data set and then use that to run molecular dynamics to generate more diverse structures as part of the second half of data generation. Finally, the last component of the data set and the largest by number of atoms is electrolytes. Now, I kind of come from the battery world, and where running DFT on electrolyte systems is very costly and very important to understand how electrolytes react, and that's really what has the reactivity of electrolytes is central to our ability to have commercial electronics. Every one of the devices that we're all watching this talk on right now is using a battery. And we really went quite crazy here as far as the number of different sampling strategies that we used. We sampled electrolytes from literature. We built quasi-random electrolytes. We ran classical molecular dynamics on these whole boxes of solvent and cation and anion and additive. We pulled kind of 3 angstrom clusters out of those MD simulations. We pulled 5 angstrom clusters out of those MD simulations. We added and removed electrons from those clusters. Those are the redox clusters. We then also scaled the distance between the molecules in those clusters because you want to kind of sample the intermolecular interactions at different distances, right? As you pull the molecules apart, you'll get weaker interactions. As you push them together, you'll get kind of stronger interactions, and the machine learning potential needs to understand all of that. Those are the scaled clusters. We also ran ring polymer molecular dynamics. I again did the AFER pipeline on a whole bunch of electrolyte reactions. We built these random solvates by sticking functional groups together and throwing solvent and ions around them to kind of do a non-MD structural sampling approach. We used the restraining potential to simulate a droplet, like you would have a bit of a liquid or an electrolyte in the air, and took clusters of molecules from the surface of those droplets. And again, we did the kind of pseudo-active learning approach of training an MLIP on the first half of the data set, and then using that to generate data for the second half of the data set with MLIP-MD.
There's a question, Manas?
Hey, Samuel, this is Manas. So just quickly on the sampling, the three different slides that you showed, was there any sort of down selection done? Because you are generating a huge amount of data, but have you done any sort of down selection in terms of, are the structures unique, or like is the information generated unique in its structure selection?
It's a great question. So, I mean, we ran quite long molecular dynamics trajectories, and then we were sampling those trajectories quite sparsely. So,
Got it.
If we're running, 100,000 time steps of MD for each system, I think, we were sampling, I don't know, maybe 1,000 frames. So they should be, uncorrelated at that point. And then from each box, I mean, we're only taking kind of chunks of the box. Yeah. So, I mean, I think when you're generating data at scale, it's quite hard. Like, I think people have championed plenty of kind of these true active learning approaches in the past, where you're really using the uncertainty of a trained model to kind of identify the structures that are worth simulating. But we had, 100,000 compute nodes running DFT continuously for like a year. I mean, it's when you're churning through, when you're generating data on that scale, it's not really feasible. Like the cost of retraining a model or even just doing inference to identify like the highly uncertain structures is not really feasible. So we just did our best. I mean, when we run geometry optimization, we would basically always cap it at like 3 or 4 steps. So because we did not want highly correlated tails, right, of structures. And then from the MD, we were always taking kind of well-separated structures from well-separated snapshots. So I'm not saying that the data is like perfectly uncorrelated, but we did our best to kind of make it as information dense as possible. And we have some, there's evidence now that I think we did a good job, as I'll come to later.
Got it. One follow-up to that is, when you did the MLMD approach, like you take the first half as the training set, you develop a potential, and then you're sampling. Is there any care taken to, like, are you going at like higher temperatures, like crazy temperatures, to make sure that like inherently the structure becomes uncorrelated in a short span? Like, is there any sort of logic there built into your workflow?
I think we did do a variety of temperatures, but we actually, I mean, empirically, we ran a bunch of testing and we saw that after 2,000 steps, the structures were very different. So we, didn't overthink it. Again, I'm not saying that at every point we made the absolute optimal decision, but we had a lot of really smart people making the best choices that they could while keeping the beast of the 100,000 nodes fed constantly.
Yeah, thank you. Yeah, I understand.
Yes, great questions. So just kind of taking a step back here, right? These are the 4 pies that I showed, and I'm just like extremely proud of all the hard work that went into this. The thing that's kind of crazy to realize is that any one of these slices of any one of these pies would have itself been a world-leading data set. And we did it all together at the same time. And that, I think, just shows kind of the level of ambition in this effort to do it all at once in a consistent manner. So, all right, so we've talked about data generation. Now we're going to talk about models and evaluations, because in order to kind of quantify, we want this data set to kind of transform computational chemistry, and we want there to be clear areas for people to develop improved models training on the data set. But before I kind of go to some of these models and evaluation metrics, I need to talk a quick aside about UMA, which is the so-called universal model for atoms that was released by the FAIR chemistry team at the same time as OMol. And I'm not an author on UMA, but obviously I'm a fan. So the idea behind UMA is that it's trained on basically all of the data sets that Fair Chemistry has ever put out. So OMol, this is an OMC, is an organic molecular crystal data set that was also kind of came out with UMA. OMAT, the ODEC, the MOF data set, and the OC20 data set. So in total, this is almost 500 million DFT snapshots that this model is trained on, which is far more than any previous MLIP. But the challenge here is that these different data sets are at different levels of theory. You can't just like mix them all together and train a model on it, because you have basically these are incompatible labels because of the different kind of software used and the different level of theory used for each data set. So you have this task embedding. And then really what's kind of interesting about UMA is that they show that if you kind of hear the single task performance, energy MAE is kind of normalized. So this is the performance you would get if you just trained a model, an isolated model on an isolated data set, okay? And then they basically try to just do a simple multitask model. And for the most part, the multitask model is just worse than the single task models. But then they added this mixture of linear experts, or MOLE, and that actually made all the performance improve. So now you're getting, the model is getting some benefit, kind of the performance of each, subdomain is getting benefit from training on all of this data at the same time. And here you can kind of imagine that the model's learning some rich representation, a unified representation across these different domains, these different data sets, and then is kind of knows how to predict the specific energy and force properties for the different tasks separately. And for OMol, you have charge and spin, but for all the others, you don't have charge and spin. So I'm not going to go deeply into UMA. You can invite Brandon Wood to give a talk here if you like. He's also been going around and talking about it, and the paper, of course, is out on arXiv. But I will be showing some performance metrics on the OMol evaluation with UMA, so I wanted to mention it here. And the last thing I'll say about this mixture of linear experts is that this allows you to have a massive number of learnable parameters, but then a much smaller number of parameters active at inference time. So that way, Meta can pay the cost of training these huge models, but then as far as a scientist taking it and using it to do their simulations, it still remains fairly fast for inference. So that's also a nice benefit of the mixture of linear experts. All right, so back to OMol land, right? Every data set needs to be split and have standardized train, validation, and test sets. So here, OMol, we have the full training set. We have the 4 million subset, which should be a uniform subset just to allow people to train on a smaller slice of the data, to allow academic groups to develop models without having to train on 100 million data every time. We also have the charge neutral closed shell or singlet subset that's about a third of the data set, because some people would prefer not to deal with variable charge and spin, and we also want to allow them to leverage the data to develop models. Then we split basically on composition. So this means that if a specific composition, 10 carbons, 15 hydrogens, 2 nitrogens, and a manganese. Like if that composition is in train, it won't be in val, it won't be in test. If it's in val, it won't be in train or test, right? So basically split on composition. This is a standard approach for molecular data sets. And so then that's our val set, is just a compositional split. And then in test, we have both the compositional split and we have 5 test sets that we have designed specifically to be out of distribution. So here we have like metal ligand pairs that are out of distribution from train. We have biomolecules containing metals, which is there are no metal containing biomolecules in train. We have held out reactions for our reactivity test set. We have the crystallographic open database for experimental structures of metal complexes. Those are the ones that I'll highlight at the moment. So now we can throw up, this is the classic machine learning thing to do, is throw up a big table with a whole bunch of numbers, and I'm going to do my best to kind of walk you through it fairly quickly. So here we have just the model trainer only on OMol, and then we have the UMA model at 2 different sizes, small and medium, right? So here you can kind of see that in general, the errors are a bit better when you train on all of the data instead of just OMol. I mean, not all the numbers, but mostly they get a little bit better. But I also just want to go right into the composition here, because here we can have some chemical intuition. Let's start with neutral organics. So kind of our largest model, the energy error is in milli-electron volt, MeV. And so for chemists, and materials people in the audience, you're probably used to seeing numbers like this. But just as a rule of thumb, if you have an energy error below 20 MeV, this is total energy, not energy per atom. Just want to be clear for the material scientists in the audience. Total energy error of 20 millielectron volts, less than 20 is excellent. I mean, your model is close to a perfect surrogate for density functional theory, and also less than 10 millielectron volts per angstrom forces. So for neutral organics, our medium, the UMA medium 1.1 is close to a perfect surrogate for kind of neutral closed shell organic chemistry, which is pretty exciting out of the box. Because one thing I want to be clear on is these are baseline models. We expect models to get much better in the coming months and years as a lot of smart people around the world develop better architectures to train on this data. This is just the starting point. And then you kind of go to biomolecules, you see a much higher energy error, a lower force error, probably because there's more reactive snapshots here where you have higher forces. And then this kind of follows our chemical intuition that electrolytes are more complex than biomolecules, and metal complexes are more difficult than electrolytes. So the biggest errors on the metal complexes. But still, for baseline models, I think we were all pretty excited to see how low these errors are. And I'll show you how useful the community is already finding these models. And then just coming back up here to the test sets, for biomolecules with metals, I mean, this is central to all of life and kind of biochemistry. And okay, 55 MeV total energy error is not amazing, but still 10 MeV per angstrom force error for these, rigorously out of distribution systems of metal containing biomolecules is quite exciting. Reactivity, much harder. The crystallographic open database also a bit harder, although still kind of on the same order of magnitude as just our composition-based metal complexes. So that's just what I just showed the tables of, are just energy and force error on these test sets. But energy and force error alone is not sufficient to evaluate a model's utility. And so another big component of OMol, besides just the data generation, was developing a novel set of evaluation tasks and metrics that are more representative of how people will actually use these models, so that we can really get a handle on how well they do for different types of kind of computational chemistry tasks. So the first one, ligand pocket interaction energy, again, kind of protein ligand binding is central to a lot of biochemistry and kind of drug development. And here we basically define just the change in energy due to the interaction between the ligand and the pocket. So you can get that by taking the total energy and forces of ligand plus pocket minus the energy and forces of the pocket by itself minus the energy and forces of the ligand by itself. And so that delta tells you how the interaction between the ligand and the pocket changes the energy and the forces. We then also have a task around ligand strain and conformers, the ability to kind of capture the global minimum of a molecular configuration. We have a task around protonation energy, kind of the ability to get the change in energy and the change in geometry as you add or remove a proton, again, central to so much of chemistry, acid-base chemistry, biochemistry. And then we also have these ionization energy, electron affinity, and spin gaps, which is to say if you add an electron or you remove an electron or you change the spin of the electronic configuration of a molecule, can you resolve the change in energy and the change in forces due to those? And that's essential to kind of oxidation and reduction chemistry, which is particularly important in kind of for metal complexes and catalysis and batteries. And then finally, we have distance scaling, where if we increase and decrease the distance between molecules, and then we take a delta between their energies and forces, how well do we recover that? Again, this is about resolving these intermolecular interactions, which can be much smaller kind of magnitude than the intramolecular, kind of the atom-to-atom interactions that are participating in a bond. But on a macro scale, it's the intermolecular interactions that often govern the properties like density and solubility and viscosity, and that really impact a solution's macro scale behavior. So again, I'm going to throw some numbers up. I'm going to move a bit quickly through these. All this information is in the preprint, by the way, and I'm always happy to answer questions over email or on LinkedIn or on Twitter or Blue Sky. Just want to throw that out there. But so these numbers, just to be clear, for the ligand strain, which I didn't describe heavily, but 2.28 MeV. I mean, this is a minuscule number, absolutely tiny, with a very, very small RMSD. The models are essentially performing perfectly. on this task right out of the box. On the conformer task, an even much smaller RMSD, and again, a minuscule energy. I mean, people, typically the community response to these numbers has been that for neutral closed shell organic systems, we have created essentially a perfect surrogate for the density functional theory that we used to build the training data set. For protonation, the delta energy numbers are now a bit bigger, 22 MeV, not enormous, but bigger, showing that the influence of charge and protonation is a bit more challenging and something that, there's a bit of room for improvement in the models going forward. But the room for improvement really gets much more clear and much larger for these other tasks. So this protein ligand interaction, we're now at an energy error of 76 millielectron volts, which is quite large, quite a bit of room for improvement. And especially much more room for improvement for this ionization energy, electron affinity, and spin gap. Again, adding or removing electrons, changing the spin, the total multiplicity of the electronic configuration. And this is probably poorly handled by the models right now because the total charge and the total spin are provided as inputs to the model, just as they're provided as inputs to DFT. But the model has no way, it appears, to learn that charge localizes. If you have 10 molecules in a cluster and you add an electron, that electron is going to mostly localize probably on one molecule. But right now, the model has no kind of description of partial charges or kind of this local change in charge or in spin. And that's probably, the source of why these errors are so large. That information exists in what we have released. So it's more a matter of there being kind of lots of room for MLIP architecture development to improve the treatment of charge and spin long-range interactions, which lots of people are aware of and are working on. And we've, I think, finally kind of given a really strong training set and evaluation metrics that will really push that development forward. Finally, for the distance scaling at short range, the errors are quite low, but at long range, especially the energy error is extremely high. And you can basically think of that as really these MLIPs, they use a 6 angstrom graph cutoff. So there are no edges in the graph between atoms that are more than 6 angstroms apart. And here the long range distance scaling task is explicitly when we have molecules sitting in space greater than 6 angstroms from each other. So we've kind of intentionally broken the models here, but it's, in chemistry, their interactions persist further than 6 angstroms, specifically kind of the Coulomb interaction based on charges. So this is, meant to highlight a clear limitation of current models, which we expect to get much better in the coming months and, year or two. So I just want to talk a bit about other kind of benchmarks that another group has done. This is specifically from the Rowan computational chemistry startup, which I'm a big fan of. And Rowan has their own kind of leaderboard where these are now all kcal per mole, or at least in this column, it's kcal per mole versus coupled clusters. So coupled cluster is kind of the gold standard for electronic structure of molecules. And what we can see here is that basically the models trained on OMol are just a step function change from everything else that came before. Across the board, much better performance on kind of this Rowan leaderboard. And a well-known computational chemistry group led by Todd Martinez, I think one of the OMol members is a friend in their Slack. And the day of release, or when they saw these numbers, they commented, take it at face value, there's basically no point in doing DFT on neutral organic molecules, ground states, ever again. But we can go deeper here. If this GMTKN55 set, it sounds like gobbledygook, but it is a kind of benchmark set that people have used to parameterize density functionals now for quite some time. And this table is just neutral closed shell organics. That's kind of the default settings on the Rowan webpage. But you can dig deeper into things, with metals and charge and open shell species. And now you can actually see that, in some cases, our MLIPs are already more accurate with respect to coupled cluster than, extremely high levels of DFT. For large systems, for barrier heights, they're basically on par for these intramolecular non-covalent interactions. It's just, you'd rather use the MLIP than run a very expensive density functional theory simulation. Of course, that's because the level of theory that we trained on is itself very, very high quality and kind of more accurate with respect to coupled cluster than this level of theory. But just to say that even for kind of these complex chemical cases, we're doing extremely well on these energy metrics. And that's why for the first time, MLIPs trained on OMol can deal with kind of really exciting cases, like with the fact when you have a copper-1 complex, the geometry should be tetrahedral. And if you have a copper-2 complex, that's say with the same ligands, it should be square planar. Machine learning potentials before OMol25 could not resolve this difference, and now they can. Another example is the ethylene carbonate molecule, which is in every single one of the batteries and every single one of your consumer electronics. And a neutral ethylene carbonate molecule should be stable, and indeed it is. But when you add an electron to ethylene carbonate, it becomes a radical anion. This basically happens in the production facility, in the battery production facility for every one of your electronics. A reaction cascade is initiated by the breakage of this ring bond, and that forms something called the solid electrolyte interface that makes a battery stable and commercializable. And again, for the first time, MLIPs can now, trained on OMol25, can capture this difference in kind of the neutral versus the radical anion form of the molecule. One thing I just want to call out briefly here is this is from the UMA paper, but that I find pretty interesting is that when they're training these single task models on the different data sets, the OMAT and OC20 and these basically all the previous non-OMol data sets for the most part, they start to overfit pretty quickly, like just like 1 or 2 epochs, and your validation error is going up. But for OMol, they don't. They just keep training. The validation error keeps going down, keeps getting better. The last I heard from the folks so on OMol, that we keep training for epoch after epoch, and the train and val, the val error just continues to fall, which is really exciting. I mean, I'm not sure if this means that the models just need to be better, or if the OMol data is just really information rich and high quality, and that's why you can kind of just keep training on it. I think there's a lot of questions here, but it's an interesting and exciting result. So just to kind of wrap up with a few examples of the community reception, it's been really, really exciting to see how enthusiastic the reception has been. Some people calling this an AlphaFold moment for computational chemistry. I don't know if I'd go that far, but it's pretty cool to hear people saying it. The folks at Rowan kind of showed that the models correctly predict relative barrier heights for these complex or these difficult metal complex reactions. The Grima group basically benchmarked on their own kind of references and confirmed that UMA has strong transferability across broad ranges of chemical space. They just released a new kind of GXTB semi-empirical approach, which they worked for years to get below 10 kcal per mole on their WT MAD2 set, and right out of the gate, our MLIPs are at about 6 kcal per mole on their same benchmarks, which is very exciting because they know how to benchmark difficult cases. And we just passed 30 citations in the first 10 weeks since release. So just to show a couple of these other things that people have been doing, 25 days after we released the data set and the models was the first paper was posted using them to do science. They were doing these complex terpene reaction pathways, and they were kind of shocked to get the kind of these minuscule RMSDs of kind of DFT versus the MLIP for the transition state structures. Very small 1.65 kcal per mole difference between the MLIP and DFT. And of course, the MLIP is 10,000 times faster than DFT. So it really unlocks a scale and the speed of simulation that could never have been done previously. We were super excited to see this. The same group then 3 weeks ago put out another paper, this time going to even more difficult reactions, these complex concerted reactions in organic molecules. Now we have P450. This is a iron-containing complex, I think, from biochemistry. We're dealing with radical ions, and the Diels-Alder, everything just worked extremely well right out of the box, which is very, very exciting. The folks at Rowan have continued to do great work benchmarking these models. Here we see this is for the kind of protein ligand binding, and so all of the models trained on OMol25 are just much better than any of the previous MLIPs. They all overbind a bit, which at first we thought was due to the underlying level of theory, OMega-97MV, because the VV10 non-local dispersion is known to overbind in many body interactions. However, GXTB, which kind of does the best on this benchmark, is also parameterized to Omega-97MV, and it's not overbinding. So that's a bit interesting. I think maybe now our hypothesis is that the lack of long-range interactions mean the models are kind of learning an overly strong short-range interaction to compensate, and that's part of what's yielding this overbinding. But again, I expect these results to improve considerably in the coming months and years. Rowan also recently put out these bond association energy results where the MLIPs kind of kick ass. And here the x-axis is time, but I want to be clear that everything on this plot was run with CPUs. Of course, the MLIPs are optimized to run on GPUs. So really, the MLIP timings should be far lower if they're run on GPUs instead of CPUs. But right out of the box, excellent against sub 4 kcal per mole against experiment, basically right on the dot as far as against other DFT, and basically leading the Pareto front as far as speed and accuracy. And just last week, the last example that I'll highlight, I was really excited to see this. This is this MLMM toolkit where people are using MLIPs trained on OMol25 to model enzymatic reactions. And there's command line tools, and they're doing all this really cool stuff. And man, people are just fast. I mean, for this to come out just over 2 months after we released the data set and the models is pretty staggering and exciting. So I think it's really showing kind of the transformative impact of the work. Just a final wrap up with just a few things that we're still not quite done with. We are going to be extending the training set, adding D-block intermediate spins, more diverse heavy main group, and noble gas snapshots, chunks of molecular crystals, and also there's a fairly substantial effort in polymers, almost becoming another one of those pies that I showed you before. We have lots of additional information that we have not yet released for various reasons. Dipoles and quadrupoles, that was just a little bit of an oops. But we also have Fock matrices, all sorts of bonding and orbital information, reduced orbital populations that we need to parse and release. We're planning to do a bunch of post-processing of the wave functions. We also have 6 petabytes of wave functions that we're working on disseminating. We have additional test set and evaluation tasks. And finally, we'll be posting a public leaderboard to encourage kind of community engagement in machine learning potential development to push forward our ability to do complex computational chemistry models. And with that, I just want to hopefully advance my slides and acknowledge everyone involved in this effort. It was a massive team effort, and that's the fact that we knew we were going to be able to release it open source is why people were willing to all come together and work on this. So also just want to acknowledge Ezra, my funding source, and thank you all for your attention. I'm happy to take any other questions.
Well, yeah, fantastic. Thank you very much. Let me just ask one question to open it up. Looking maybe next 5 years as models, as I guess progress evolves, do you see what progress do you see on like the modeling side of this data versus expanding the training set to cover more regions of the chemical dynamics space?
Great question. I mean, I'm personally very interested in using these MLIPs to build chemical reaction networks, to pick apart complex reactive systems. This is kind of where I came from and what really makes me excited. There's so much of chemistry where you're dealing with hundreds or thousands or even tens of thousands of reactions all happening at the same time. And we really need models like this where we can rapidly enumerate reactions and calculate reaction barriers in order to kind of characterize and simulate those types of systems. And those go from atmospheric chemistry to carbon capture to catalysis and chemical synthesis to battery electrolytes. I mean, just so much of kind of where we need to make technological progress comes down to controlling complex reaction cascades. So that's what I'm really excited to do with this. I think, and that's why I think, unsurprisingly, a lot of the examples that I show that we've seen immediately are around these transition states and reactivity. That's kind of where I'm not the only one who sees this as a really area that this opens up. As far as to expand the training set, I mean, I think that in the materials side of things, there's still quite a good amount of stuff to be done. Defects, amorphous materials, kind of solid interfaces. On the molecular side, what we don't have right now is molecular systems with direct metal-metal interactions. And we specifically avoided those because they can often be highly multi-reference, or where kind of our best levels of density functional theory don't do very well. So I think that there's room to extend the training set there. And then also just to fine tune the models. Like if we had a couple 100,000 really high accuracy couple cluster calculations, you could just fine tune these models. It may be that, I think at a certain point, and we may already be there, it may be that we don't need to keep making the big pre-training set larger. It may be that the models are already kind of sufficiently general with a rich learned representation that everything kind of becomes a fine-tuning problem. So then you can bring in 20,000 snapshots of excited states and fine-tune the model on that, and then use it for excited state chemistry, for instance. I think it remains unclear kind of where we're going to need more large-scale data generation versus where we can just fine-tune the models. I think that's a big question going forward.
Cool, thank you. Are there any other quick questions on the call? Oh, yeah, go ahead, Manas.
Samuel, just to pick from the first comment you had with respect to amorphous materials or more complex solid state interaction, in your knowledge, is anyone else looking at it at the scale that you have done for the molecules, or is it something you are planning to extend into eventually?
It's a great question. I mean, I'm very much a chemist, right? I'm a molecular DFT person, so I will not be the one doing that.
Okay.
I hope that the team at Meta does it. The reality is that like there are other teams, like as I said earlier on, the tech company level resources are just critical for doing efforts on this scale to really generate large amounts of high quality training data. But also most of the other tech companies besides Meta, and there are exceptions. You know, I mentioned that data set from the team at Google, but there have been kind of high profile efforts from Google and Microsoft where they talk about generating a large amount of data, but then they don't release it. And so, I mean, maybe there are people working at other companies to build these data sets, but I'm an academic, right? Like I'm all about open source and people being able to use these tools. I want to see data like that generated and released. So, you know, I hope that kind of other companies can learn from Meta's example as far as the impact that this team is having, and you know, hopefully also contribute to kind of open source data set releases. But you know, I think there's lots of interest in this type of stuff. Certainly in academia, the question is where the appetite exists in industry to really kind of put your money where your mouth is and generate the data and put it out there.
Okay, so it's a question of incentive, I guess. Thank you.
Yeah.
Right, and Victor? I think Victor is unmuted, but we can't hear him. So, okay, Charlotte Barrow? Charlotte Barrow, do you want to unmute? Maybe I didn't. Okay, there's any other questions? Because it looks like they're not. All right, well then, maybe since we're at time, oh, there you are.
Oh, okay. Thank you so much for hosting this, and Professor Sam, thank you so much for this comprehensive explanation. My question, it's kind of like because I'm actually a master's student, but I'm really interested in things like these. I'm actually working on electrolytes right now. So seeing this massive data set, and actually coming from Africa, where we don't actually have access to all these supercomputing clusters, these data sets will really go a long way in helping students like me in and researchers generally. So, but what I kind of want to ask Professor Sam is, if I'm working on electrolytes, for instance, what are the ways or what kind of sort of ideas can I actually use this data to do some research? For instance, if I want to understand maybe in sodium ion batteries or sodium batteries, for instance, if I want to understand the characteristics of the electrolytes or finding the right electrolytes that I can use for in sodium ion batteries, what are the ways that this data set can help me? I don't know if you understand the question.
Yeah, no, it's a great question. And as it happens, we're actually working on wrapping up a sodium ion electrolyte specific paper using these MLIPs right now. So, I mean, what we're doing is we're running molecular dynamic simulations to simulate densities and structure factors and RDFs to understand. And right now we're mostly focused on benchmarking to see how well the models capture, ion interaction, ion solvent interactions, experimental densities, things like that. But I mean, my hope is that either we already or very soon will have models that can accurately predict density and structure factor and viscosity and ion transport and conductivity, right? And then if you could imagine what I'm imagining, what I'm hoping to work on is kind of coupling, if we have predictive models for those kind of bulk features for liquid electrolytes, and we can couple that with predictive simulation of the SEI formation, right? Like that really becomes a transformative tool for battery, kind of battery research, where you can, because in the context of batteries, especially the interface formation is extremely difficult to characterize experimentally. It's an area where kind of simulations need to lead. And so if we have predictive models, then they can lead. You can imagine screening thousands, tens of thousands of different electrolytes to find ones which kind of have a predicted set of kind of properties that are promising for the battery system that you're trying to develop, and hopefully guide experimentalists to actually synthesize and test some of these systems. So it's still going to be a lot of work, but I only kind of have a handle on like one little slice of battery chemistry, but I think that there's lots of opportunities here for using these models to get atomistic insight into systems that are really valuable for energy storage.
All right, thank you.
Yeah, and I'll observe one thing. You're pointing out the UMA has the mixture of experts model, which is, for inference time is not, it's pretty cheap. So that's the transformation, that you can shove that model inside of a Bayesian optimizer to search the space of possible structures, or a fancier optimizer. But you need, relatively like a few GPUs at most to run that. You don't need a cluster.
Yeah.
Yeah. Fantastic. Well, thank you very much, Samuel. It was a brilliant talk and like fantastic data set.
Thanks so much, and thanks for the invitation, and thanks for the great questions.